All right, let's write a script that implements actually the NIPALS algorithm. We will do it also in an iterative way. First of all, I will implement the part that only can estimate the PC1. And I will also show all the steps that I've shown you before, like the plots, the scatter plots, the position of principal components, position of projections, and so on and so forth. And then we gradually improve our code, and at the end we will create a dedicated function that can calculate all the PCA results. And first of all, it's the scores and loadings. Okay. So as you can see that I already actually added the data values. I simply copy paste the data values from my slides, and I will use the same example with weight and shoe size. Okay. As you can see, I have the data values as a separate variable so far, separate vector. So first of all, I need to combine them together. I will use cbind to make this columns of a matrix. So as I say, cbind weight and shoe size. And then if I run it, I need to run this first. And then if I run it, then I also need to correct a typo. Then I will get X as a matrix with 9 rows and 2 columns. And then you can see that indeed I have shoe size and weight. It's exactly what I have shown you before. Right? Now if I make a plot, for X, the scatter plot, you can see that actually we have some spread of the data points. But if I make the same limits, let's say, you can see that the largest number is probably 100, right? So if I use the same limits between 0 and 100, and also for the y, use the same limits for the y, you can see that the data points is actually, first of all, they're far away from the origin. And also you can see this is the direction of the maximum spread, which does not cross the origin, right? So what I need to do, I need to center the data. Strictly speaking, in this case, I also need to scale the data, to standardize the data, because I have different units and different variation of the variables. But let me use only mean centering so far. So the first thing, the step number 0, let's say, and it's a mean centering. Well, we already know what to do. There is a function scale that can does actually both centering and standardization. I need only centering, so I will simply say scale of my data X, and then center. Center is true and the scale is false, so I don't need the scale so far. Yeah. So now if I run it, and if I make it the plot again, in this case, of course, I probably don't need 100. I will probably need minus 50 and 50. That would be my best guess, because I simply move the center to the almost middle point, right? So let me see if I can actually show this. And then you can see indeed now this is the origin. I can show the origin, where the origin is. AB line H equal to 0, and then AB line V equal to 0. So I'll show the coordinate lines. You can see that now the points are exactly around the origin, right? We still see that this like a flat structure because of the different variation, but let me just live with that. Okay. So that's the first part, mean centering. I will remove this code, so I don't need it in my NIPALS. And now the next part. The next part is to find a column in your X which has the biggest variance. You remember that variance is just a squared version of standard deviation, so I can actually compute standard deviation instead of variance. It will be the same. But I need to compute standard deviation for every column of X. How to do that? Well, we know how to do that. We can just use a function apply. Function apply allows us to compute any statistic for any part of the X for rows or for columns. So I simply say apply X to columns. This margin equal to 2, it's a columns, and then I say standard deviation, right? Then you can see I get 2 standard deviations. I need to find the maximum, and I don't need to find the standard deviation itself. I need to find a column where it's the biggest one. To do that, I use a function which max. It finds actually which is the index, the position of the biggest value. And you can see it's 1. It's exactly what I need. Then I will simply say that the column index is this one, right? And then what I'm going to do, I will make the initialization of my score just by taking the values from this column, right? So I simply say X, and then take everything from this call int. And since I need this score as a vector, as a matrix with one column, I will say drop equal to false. So do not drop the dimension, right? Then if I run this and then look at the t values, you can see that it's the same as the centroid weight values, right? We have absolutely the same. Okay. Now the next point, this is my initialization. Let me call it initialization. Now the next point is to compute the loadings, right? So compute loadings. And we remember that how we compute loadings. We simply take a product, a cross product. So the loadings is just a cross product of matrix X and the T, right? Let me show you the loadings first. So this is the loadings. But I can also show you actually the other way to compute the loadings, right? So I will say P is a covariance between X and T. So it will make a covariance matrix between X and T, and then let's see for the covariance matrix. Look, this is almost the same, but of course, I mean, these are the values I have shown you, right? Why we have different values? Because I didn't divide to n-1 here. I need to divide to n-1 to get the covariance here. I don't need to do that because I will normalize the vector later. So you can see that actually cross product of mean centroid X and T, it's the same as just the covariance between them. So what we have in the coordinates of the P, it's the covariance. Which way to use, it's up to you. I think cross product is a little bit faster, so I will keep the cross product. Yeah? Now I need to divide P to the length of P. And I know I can find the length of P by taking a sum of squared coordinates, right? So if I square the coordinates and then take a sum, I will get the length of P, right? So this is how to do that. And then I know that I also need to take a square root, of course, otherwise it will be a squared distance. So this is the length of the vector. And then if I want to normalize my vector, I simply need to divide every coordinate of this vector to this normalized value, and that will be my vector P. And then you can see again, it's absolutely identical to what you have seen in my previous videos, right? Now let's visualize this P on this plot. So how to do that? Well, first of all, I think it was a bad idea to remove the plot after min-centering data, because I'm going to restart my script and then this plot will disappear. I need it to show the position of the loading, so I will just get it back. Here we go. I'll just run all script just to make sure that everything works fine without any errors. I got this one. I will add the coordinates, the coordinate lines. AB line V equal to 0. Yes. Then I'll also probably add a grid so we have a better representation here. So if I click source, I should get the plot, right? Now look, let me just change perhaps, I don't need minus 50, right? I need probably minus 25 here and then plus 25 here. So I will make it a bit bigger so it's a bit better to see the behavior of the points. So once again, now it's almost perfect, right? So now look, let me visualize. How to visualize this? Well, first of all, of course, you can just use function arrows, right? Arrows, and then you remember 0, 0, and then P1, because it's just two values, I can just do it like this. So this is the arrows, right? But you can see it's very tiny. You don't see the arrows actually, because it's a very small one. So what you can do, you can, for example, multiply it to 100. It doesn't change the orientation, right? But it will change the length. Then you can see that's the arrow. But in this case, I see it only in one direction, in the positive direction. I don't see it in the negative direction. What you can actually do instead, you can think about computing a slope. You can think about this vector, it's a line, where slope it's a ratio between y coordinate and x coordinate, right? And the intercept is 0. So I can actually do it like this. I can say AB line, and then A equal to 0, that's the intercept, and B, which is the slope, it's the second coordinate divided to the first coordinate, right? Then I will make it red line. So now we will get the perfect orientation, the perfect visualization of the PC1, right? So this is the PC1. Okay. Now look, now we need to compute scores, right? So we say compute scores, the new scores, and then T equal to, and then it's simply projection, right? So AX and then times P, right? And then this is the new scores. You can see again, we have a bit different scores. Now it's instead of 12, we have 12.14, then minus 4.66 instead of minus 5 and so on. But that's how it is. If I want to visualize scores, I need to compute the coordinates of the scores in the original space. So this is position along PC1, right? It's a position along this red line. If I want to visualize scores, I need to compute the position of these projection points in the original space. And luckily we know how to do that, right? So we can say just compute TPT, right? TPT is, I just use T cross prod. T because I need to transpose the second part, right? TP. And then look, I can add points. I say points, TPT. Let me use another, let's say, point character, and then I use color equal to red. Oops, red in quotes. Then you can see these are the points, right? So you can see the projections. So these are the projections, okay. So now what I need to do now, I need to go back and do it again. So now I have new scores, I have new loading, so I need to run this again. So I just run it. And then look, because I didn't change the plot, we will see it on top of this plot, right? So you can see that I don't think you see that, but actually this is a new line. It's a little bit different from the previous one. You can also see it in the coordinates of the vectors. But the difference is so tiny that you barely see it. Okay. And then I can compute, let me just keep it like this. Then I compute new scores. So these are new points. Again, they are almost identical. Then I go back and do it again. So you can see again, if you compare these two, let me show you. So you can see 9755706, 9755669. So the first four values are the same, decimal points, decimal values are the same. Here we have 219600864, 2197026. So you can see it's almost the same. And then I can repeat it again, repeat it again, repeat it again. However, in R, we know that we can repeat several things, the same code several things if we use a for, right? So the for loop. So instead of doing this, I can just write for, let's say I will use, in this case, 10 iterations. Okay. Of course, later we can define the convergence criterion, but so far let me use 10 iterations. And then just move it back, move it in. And that's actually it. So now we can just, I think, remove all these extra things where we visualize the data. So look. And of course, we don't need the initialization part inside the loop, so I have to move it down, move it out, right? So look, first we initialize the values. Good, find the column with biggest variance, get an initial estimation of scores, and then compute loadings, normalize, compute scores, compute loadings, normalize, compute scores, and that it will be done 10 times. I don't have convergence criterion here. I just say, okay, do it 10 times, and then the result will be here. I don't need this one as well, right, so far. So this is how it looks. This is actually NIPALS, right? This is actually NIPALS.